This video is about an application of maxima and minima. The topic is called optimization because we will try to get the most effective or the best solution for the problems. What we're going to do here is we'll obtain the maximum or the minimum value of a function. But first, we have to set up the function that will either maximize or minimize. Here is the first problem. So after reading the problem, we'll set up a function of one variable only, and then we'll identify whether we'll maximize or minimize that function. The sum of two positive numbers is 60. How can we choose them so as to maximize their product? So first, let us identify our variables. We have two positive numbers involved in this problem. Let x and y be those two positive numbers. Alright, and since the sum of these two positive numbers is 60, then we can have the equation x plus y equals 60. Now what we want to do is we have to choose these numbers x and y so that their product is a maximum. So if we get the product of x and y, and let p be this product, then we have to maximize this function, p. Right? Maximize p equals x times y. But we have to write p in terms of one variable only because we have to differentiate this later on to get the maximum value for p. So because we have the relationship between x and y here, we can either write x in terms of y or the other way around. We write y in terms of x. Right? So from this equation, we can write y in terms of x by transposing x to the other side, and y will be equal to 60 minus x. Okay, now the function p in terms of x and y can be written in terms of x only because y is equal to 60 times x. So p now would be in terms of x only, and we'll call it p of x equals x times y, where y is equal to 60 minus x. 60 minus x. And then we'll simplify the function by removing the grouping symbols, and we'll have p of x equals 60x minus x squared. Now we'll try to get the maximum value for p by getting the first derivative of p. So p prime of x is equal to 60 minus 2x. Now remember, to get the maxima or the minima of a function, we equate its first derivative to 0. So equating p prime to 0, we'll get 0 equals 60 minus 2x, and then we'll solve for x from this equation. Okay. So transposing 2x to the other side, we'll have the equation 2x equals 60. Now isolating x on the left side, we just simply divide both sides of the equation by 2, and we'll get x equals 30. Now since we have the relationship of x and y over here, we can get the value of y. Now we have the value of x. Y is equal to 60 minus x, where x is 30. So y is equal to 30 also. Now first, before we consider this as our final answer, we have to check whether x equals 30 is a maxima of the function, or rather, if it will lead to a maxima of the function. Using the second derivative test, recall that the second derivative of the function at a specific value of x must be less than 0 to consider that this value for x will yield to a maxima of the function. So we need to get the second derivative of p of x. So p double prime of x, this is the first derivative. So for the second derivative, we'll have negative 2. So this means that for whatever the value of x is, p double prime of x is always equal to negative 2 because it's just a constant. And obviously this is less than 0. So therefore, x equals 30 will yield to a maximum value for the function for p of x. So the product of x and y, these values, 30 and 30, will lead to a maximum product for the two of them. So it means to say that 30 times 30, which is equal to 900, is the maximum product for two numbers whose sum is equal to 60. So our final answer would be x equals 30 and y equals 30 also. Here's another example similar to example number 1. Find two positive numbers whose product is 64 and whose sum is a minimum. So the next step is to define the variables that we will be using. So this problem involves two positive numbers. Let x and y be those two numbers. Alright. So now, the product of these two positive numbers is 64. So if we multiply x and y, we get 64. And we want a minimum sum for these two numbers. Okay, so we have to choose these two numbers so that their sum is a minimum. So we are trying to minimize the sum of x and y. So what we're going to do is minimize the sum, let's just call it s, of x and y. Okay, so we are trying to minimize this function. Now we have to write the function s in terms of x or y only. So if we choose to write the function s in terms of x only, we can get the relationship between x and y from this first equation. Okay, we can write y in terms of x by dividing both sides of the equation by x. So just divide both sides of the equation by x, and we get y equals 64 minus x. Therefore, we can write s in terms of x only. Okay, that is x plus y, where y is 64 over x. Alright, since we are trying to get the minimum value for the function s, we will get the first derivative of the function, s prime of x. So we are differentiating s with respect to x, and we'll get 1 minus 64 over x squared. Alright, so to get the minimum value of the function s, we will equate s prime, or the first derivative of s, to 0. 0 equals 1 minus 64 over x squared. And then we'll transpose 64 over x squared to the other side of the equation, and we'll get 64 over x squared equals 1. And then multiplying both sides of the equation by x squared, we are trying to solve for the equation now. We are trying to solve for x. So we'll have 64 equals x squared on the other side. Now, isolating x on the right side, we have to get the square root of both sides of the equation. And from there, we'll get x is equal to plus or minus 8. But remember that x and y are both positive numbers. So we eliminate negative 8 already in the equation. So x must be positive 8. Now, before we get the value of y, we have to check that 8 will yield to a minimum value of the function by using the second derivative test again. Now, in the second derivative test, of course, we need the second derivative of s, denoted by s double prime of x. We'll try to differentiate this function this time. Okay, the derivative of 1 is 0. And then the derivative of negative 64 over x squared will give us positive. So plus 128 over x cubed. I just used the power rule to differentiate negative 64 over x squared. You try it yourself, okay? Now, the value of s double prime of x at x equals 8 must be greater than 0, so that we can conclude that x equals 8 will yield to a minimum value of the function. So at x equals 8, s double prime of 8 is equal to 128 over 8 cubed. Okay, we don't need the exact value of this number anymore, but what we want to see is that if s double prime of 8 is a positive number or a negative number. So obviously this is positive, which is greater than 0. So therefore, x equals 8 will yield to a minimum value of the function s of x. So therefore, if we choose x to be equal to 8, okay, since the relationship between x and y is equal to 64 over x, then y is equal to 64 over 8, which is also equal to 8. So we have x equals 8, y equals 8. Now these two values will give us the minimum sum. And of course, we have to remember that the product of these two numbers must be 64, and 8 times 8 is 64. Okay, 8 plus 8 is 16. So this is how we choose two numbers whose product is 64 and whose sum is a minimum. Well, you can try other combinations of numbers like 64 times 1. Those are two positive numbers also whose product is 64. But if we sum them up, we get 65, right? So let's say, for example, x is 64 and y is equal to 1. Their product is 64, but their sum is equal to 65. Or if x is equal to 32 and y is equal to 2, their product is also equal to 64, but their sum is equal to 34, which is quite bigger than 16. Okay, you can try the other combinations also, and you'll see that the minimum sum for these two numbers whose product is 64 is 16, and this is how we choose those two numbers. Okay, this is problem number 3. It's one of the most common problems that you'll encounter for the application of maxima and minima. So number 3, a box is to be made from a sheet of cardboard that measures 12 inches by 12 inches. The construction will be achieved by cutting a square from each corner of the sheet and then folding up the sides. Find the volume of the largest box that can be made in this way. So before we define our variables, it's easier if we draw the figure of this problem. Alright, so in this figure, we have a sheet of cardboard whose sides measure 12 inches. Okay, 12 inches. Alright, from this sheet of cardboard, we are to make a box. Okay, by folding up the sides. But first, before folding up the sides of the sheet of cardboard, we have to cut a square from each corner. Okay, so we cut a square from each corner. Right, look at that. And from there, I defined a variable x already without using words. Okay, but by using this figure, it's clear that this is a square because each side measures x. Alright, so upon cutting those squares from the corners of the cardboard, we have to fold the sides of the cardboard to make this figure. Okay, to make this box. Okay, so since we have cut x here from this side of the cardboard and x also from the other side, then this remaining portion is just 12 minus 1x that we cut from the left side and minus x again that we cut from the right side. So this is just equal to 12 minus 2x. Alright, so that's why this side of the box just measures 12 minus 2x units. Okay, now for the other side of the box, remember this is still a square box. So this side, again, measures 12 minus 2x because we have got x here and x also from the other side. Alright, so this side of the box and also the other side also measures 12 minus 2x. And because we have cut a square from each corner of the cardboard, this measures x units. Okay, so when we make this box, the height of the box, this will also be x. Alright, so what we'll try to do here is set up a function, and that function must be maximized because we want to find the largest volume of the box that can be made from the given sheet of cardboard. Okay, so we have already defined our variable by the figure, by using the figure. So the next step is to set up a function that will try to maximize. So we want to maximize, so we want to find the largest volume, okay, of the box. So we want to maximize the volume V of the box. Alright, now we have to identify the formula that we need to find the volume of this box. Okay, so since it's in the form of a rectangular prism, to find its volume, we just need to multiply its length and width and height. Okay, so V is just length times width times the height. Okay, but we have to write the volume in terms of one variable only, and we can do that because the length here is written in terms of x, and also the width is written in terms of x, okay, and also the height is written in terms of x. So V in terms of x is equal to length 12 minus x times the width 12 minus 2x, sorry, and then the height is equal to x. So length times width times height. Alright, we'll simplify the function first. So v of x equals, by FOIL method, so this will give us 144 multiplied by x here, 144x. And then the middle outer terms, this is going to give us negative 24x, and this will also give us negative 24x. So if we add them, we get negative 48x multiplied by x again here. So it's x squared. And then the last terms, this will give us positive 4x squared multiplied by x again. We'll have plus 4x cubed in the last term. Okay, now we're ready to differentiate this function. Remember, to get the maximum value of the function, we have to get its first derivative and equate the first derivative to 0. So v prime of x is equal to 144 minus 96x plus 12x squared. And then we'll equate the first derivative to 0 to get the maximum value of the function. So 0 equals 144 minus 96x plus 12x squared. So everything is divisible by 12, so we can factor out 12 from all the three terms on the right side. And we'll get 12 times the quantity 144, not 144 anymore, 12 minus 8x plus x squared. Okay, or we can write this as 12 times x squared minus 8x plus 12. And then to solve for x in this equation, we just have to factor this trinomial if it is factorable, or if not, we can just use the quadratic formula. Okay, so equating this to 0 afterwards, we can solve for x. Alright, so factoring, we'll have the factors x minus 6 and x minus 2. Okay, factoring x squared minus 8x plus 12, we'll have these two binomials as factors. Okay, now equating x minus 6 to 0 and also x minus 2 to 0, we'll get two values for x. One is x equals 6 and the other one is x equals 2. Now, this is not a possible solution anymore. Why? Because whenever x is 6, remember what is x? X is the side of the square that will cut from each side of the cardboard. Now, if we cut from here, if we cut 6 inches and then 6 inches from the other side, nothing will be left of the cardboard, right? So this is not a possible solution anymore. So we'll just check if x equals 2 is yielding a maximum value for the function v. Okay, by the second derivative test, we'll get the second derivative of the function v double prime of x. Right, let me just write that this is a second derivative test. V double prime, this is v prime. V double prime is negative 96 plus 24x. Alright, so at x equals 2, what is the value of v double prime? So that's negative 96 plus 24 times 2. So that's negative 96 plus 48. So this is a negative number which is less than 0. So if v double prime of x is less than 0, we conclude that x will yield to a maximum value of the function. So therefore, x equals 2 will yield to a maximum value of v of x. So if x is equal to 2, then the height is equal to 2 inches. And then the length is equal to 12 minus 2x. So 12 minus 2 times 2. So we have the length equals 12 minus 4, so that's 8 inches. And then the width is also 12 minus 2x. Okay, so 12 minus 4 is 8 also. So the width is 8 inches. Alright, so these are the answers. So the question, make sure that you answer the question. Find the largest, the volume of the largest box that we can make from this sheet of cardboard by doing what we did. Okay, so the volume is equal to length times width times height. So it's 8 inches times 8 inches times the height 2 inches. So we're going to get, so 8 times 8 is 64 times 2, we get 128 cubic inches. This is the volume of the largest box that we can make from the sheet of cardboard given.